Could we do the, turn the hanging mic on, please? Support, thanks a lot, man. Appreciate it. Test, test, test. Okay, there it is. All right, so we've got the final session. We're going to finish the session on, basically, Michael started it off. The title, we forgot to mention the title of the session is kind of comparing SQL and NoSQL type environments, so trying to drive workloads related to processing data. So historically at this conference, processing data has been primarily kind of raw HPC types of data or HPC structured data. So this session we're talking a little bit, we're focusing a bit on business type databases, but also just very large scale systems to manage small files and how to analyze the data. So this is the first time I presented these particular slides. I'm working in cloud infrastructure. These slides are from PM, so I stole them from the folks mentioned there. There's a couple of, I'll just throw in whatever, so Oracle, we do cloud. It's a bunch of great things about it. We have a big cloud and lots of data centers, lots of people are using it. It's growing fast. Okay. All right, so let's get to technology. So the technology is, that I'm going to talk about in this session is, in my talk is Exadata. Somewhere somebody cloud washed the Exadata, so all the discussion of Exadata here will say cloud, but it's actually correct because Oracle's database in the cloud is essentially driven by Exadata. So Exadata is basically a database appliance. So it runs the exact same database software that you can run on IBM, HP, or whatever generic hardware you've always been able to run Oracle on. So what does it look like? Well, it's very interesting. It's one of the coolest things. Technologies that I've seen at Oracle, and there's a lot of good ones, as you've heard already, and that's really why I'm at Oracle, because there's a lot of great technologies that help solve real problems. So I wonder if does this have a pointer? Does that pointer work? A little bit, okay. So basically it's sort of a two-tier architecture. You've got a tier of servers that run the actual Oracle database. Those others are database servers. Each server can have multiple instances. The latest release of Oracle is multi-tenant. So one can have a single sort of basic, sort of database infrastructure and then have multiple Oracle databases live within that single infrastructure. So you get essentially a virtualized database sort of infrastructure. You can run those virtualized databases as a pool across all these database servers. There's something called ASM. ASM is essentially the storage management layer. So it's kind of like a combined volume manager file system, except it doesn't really work that way. It thinks more at kind of the database level and the database block level. But what it does is it sort of virtualizes from the database server perspective what's going on down here at this bottom tier. So the bottom tier are a bunch of components called storage cells. So, and that's exactly what they are. They hold all the actual storage where the database itself resides. But they're more than that. They actually have, Oracle implemented something called function shipping. So if you were back in the day in the 90s, late 80s, early through the 90s, there was a big discussion in databases about how do you make databases scale? Do you do shared nothing? Do you do shared everything? Oracle's approach is more of shared everything, but tiered like this. And one of the ways to make things really scale well is to move the workload of doing queries and scans and joins and all that other sorts of stuff directly into the storage server. So what do you think the advantages of doing that are? So if I have a database request up here in the database server layer, what if I package it and send it down to the storage cell layer? Why is that helpful? Can you think of any reasons?
You don't have to pull all data back across the net.
Exactly. So I can basically do that database processing directly in the storage cell, and then I don't have to push it across this network. That's exactly right. So in addition to that, it turns out we use InfiniBand and we use RDMA pretty much at every point that you can possibly use RDMA. And there's a couple of protocols. I'm still learning Exadata, to be honest. I've learned it to a certain level of technical detail. But bottom line is we run our own protocols right directly across the InfiniBand. So they're low latency, very high bandwidth, lots of other cool features you can. And then as you'd expect with this kind of systems, you can scale out, more or less you can scale out the server tier layer as you wish, and storage cell layer as well. So up until recently, they were sort of fixed configurations, but if you have a heavier compute load, you can go with more database servers, fewer storage, and then vice versa, more storage. You can add, if your workload is more storage or query intensive, you can add more storage cells. Okay, so that's the basic architecture. Any questions about that? Is that helpful? Makes sense? Okay. All right, so this database cloud platform, you really want something, so let's talk about databases in the cloud. So really that's where scale is happening these days. Most places, there are a few customers that have very, very large scale Exadata systems. One is Customs and Border Protection. It turns out whenever you enter the US or leave, be you a US citizen or not, it's tracked by the Customs and Border Protection. If you're shipping something in and you have to pay duty, all this is tracked in a giant system of something like 60 of these, of the largest. So go back to the previous slide, the largest system you could have, which is a full rack, and then there's 60 racks, some enormous numbers of racks. And then there's apparently another government agency that has an even larger system. Most banks have this that use Exadata. It's how they run most banks, really large companies. So it's kind of it's something you probably haven't heard of, but but it's pretty much running the enterprise. What's kind of cool is stuff we've talked about in this conference for years. It's this community, large-scale parallelism, et cetera. I'm telling you, it's used every single day by the biggest companies with technology. Not just this, but there's others, but this is one that it is. So people are now going to the cloud to get even more scale. They want to get the same or better performance. They want extreme availability. They want to maintain the quality of service for all their tenants, and they want it to be fully secure. So how do we do that? I think it's another marketing slide. So this is the usual Oracle. So one of the cool things about Oracle is, Larry Ellison runs a company, and he just loves to bash competitors. So we get to actually bash competitors. It's a lot of fun. But I'm serious. He actually, if you read, I read a history of Larry. He he talks about picking a fight with Microsoft over the network computer. And, the network computer was kind of like you remember that, back in the late 90s? So it created all this press. He could care less about the network computer and even said so. What he wanted was, to get in a fight with Microsoft because he knew they were going to start building databases and they were going to start building all sorts of stuff to compete with Oracle. So anyway, so we have to beat up the other guys. So what our viewpoint is the new cloud databases are quite primitive. They're really 30 years behind the state of the art in terms of SQL, full support for SQL, transactions, analytics, all this other stuff. Now there's some mature databases that are deployed in the cloud you're seeing from companies like IBM, et cetera. But again, they're really not fully caught up with where we're at. So we think we're pretty awesome, So where does all this awesomeness come from? So let's go into the technical bits. So if we're going to run database workloads in these hardware-oriented systems, I'll say cloud, but it's really Exadata. There's sort of two kinds of workloads you typically have here. One is online transactional processing workloads. That's lots of small random IOs, low latency, predictable response times. That's what you're looking for. Data warehouse, a little bit different. This is lots of data to load and process at once. And you ultimately want succinct results in a reasonable amount of time, but you don't necessarily have to have the absolute lowest latency. And then test dev workloads, you want to quickly provision stuff. You want it to be simple to manage them. And then similar performance characteristics as production. So again, OLTPs, lots of users, lots of messages between these servers, lots of small updates and deletes. Consistent response times are very critical. These are typically driving a business. If you're Customs and Border Protection, if you can't do a check if this person's on a terrorist watch list very, very quickly, they're going to sit there. And then they're going to back up all the other people behind them. If you're a bank, you want to, typical things. So constant uptime is very important. So to make that happen, with traditional systems, like the ones I used to build GFS on and what you see a lot of cluster file systems built on, they're using traditional components. They've got a server layer, classic SAN, storage area network, maybe some kind of faster Ethernet, storage controllers with their RAID controllers, all that sort of stuff, and then within that sort of proprietary protocols and SCSI. So the IO sort of path has always had many, many layers of translation virtualization. It's sort of been fun, it makes our life interesting, but it also means that the software stack is pretty onerous. You've got everything, you start at the database, you go to the OS and the network stack, device drivers, the HBA, switch fabric, storage controller software, and then whatever's happening down on the drive. Drive has its own set of things. So it's a lot of stuff, and what that means is if you're trying to drive things low latency, fast, bad things start to happen. For one thing, if you're building out one of these database clusters, the database to day server communication happens on slow 10 gigabit per second Ethernet. So Ethernet is hugely popular, we all love it, but it has high latency and low throughput compared to other networking technologies like InfiniBand, which is a 40 gig per second network. It's coming, and 100 gigs per second is coming. It's got lower latency. You can do zero copy RDMA through it, higher throughput. So traditionally, things like RAC, this database to storage communication, so this part of the path, is traditionally done over fiber channel. I love fiber channel. It's always been a pretty cool technology, but it's shared storage, so it's unable to take care of this higher bandwidth and lower latency types of networks. The number of HBs on the database server limits performance. And then compared to InfiniBand, which enables a lot lower latency and then higher IOPS for OLTP. So InfiniBand's critical to really driving this. So if you kind of build the big picture here, this traditional networking stacks delay the ability to communicate across multiple servers doing the, running the database protocols. And then this really makes it difficult when you're doing OLTP. The messages are small, they're relatively simple. They don't really require a lot of time to go through the network and execute on a destination. So really, what really drives most of the latency there is going right through that stack, going through the CPU and OS, and then traversing that big layer. So the network stack's pretty significant there. If you go with a InfiniBand kind of network, a bunch of good things happen. You can enable low latency, higher bandwidth. You can basically use a specific protocol that we do to basically drive things, and it's custom designed for critical OLTP workloads and specifically bypasses this OS and networking stack. Also, the InfiniBand hardware primitives are called directly from the Oracle software, and so ultimately what you end up with is just huge amounts of that networking stack or overhead are taken out. And then you can start layering this and start doing even more interesting things. An important thing with online transaction processing is you love Flash because you get the performance, but we hate Flash because every once in a while it decides to do garbage collection or it has some kind of error correction it has to do. So it has these spikes in response time, which are bad. Again, we're trying to serve very low latency very consistently. So we want to use Flash, but we want to hide that. So Flash arrays try to hide it with a DRAM cache with a UPS backup. But these tend to fail when you've got a big surge in I/O load. It tends to be an issue. So even with the DRAM cache, the workload it doesn't fit in that cache, and you're still exposed to some of these outlier response times from the Flash. And it's particular in databases, you typically keep the thing consistent by writing through a log. The log contains all the changes to the database. That can be a lot of stuff, especially if you're logging data as well as metadata. So log writes can really be a key bottleneck. So what happens is a small change in this log response time based on Flash, doing garbage collection or something like that can lead to large slowdowns in the commit latency and then OLTP throughput. So you see that here, these spikes that occasionally happen. So what you can do, though, is very simple process. Go ahead and write to 2 log devices in parallel. And so as soon as the first one completes, then you can respond that you're done with the process. So if one of the Flash devices starts to go into one of these modes that increases response time, you can use the other one, and the result is the spikes go away and the overall latency drops by about 1/3, 3 times. Okay. All right, there's some more examples here, but I don't have enough time. Here's another challenge. So again, the theme here, I'm covering a lot of room and ground in a short period of time. We want to integrate the hardware and software very tightly. We want the database software, the OS, to understand the hardware very deeply. And then we want to take the benefits of that convergence and feed it back to the workloads. So big problem in databases is, well, everybody loves going back to their data and running big queries on it and trying to analyze what the heck's going on. Traditionally, you'd have to take your existing kind of online OLTP database and you'd create sort of a cube and something you would put into a separate data warehouse and start analyzing it there. Well, what if you could do the same? What if you could basically run data warehouse queries on your data live? So you're still serving out OLTP, this transactional stuff to keep your production workload going, but you could be analyzing the data in real time. The problem there is this mixing of workloads degrades response time. So typically, if you just run OLTP, you're fine. you've got the whole machine to yourself, and you're getting mostly these small lookups and updates, et cetera. But when you do all this classic workload, you've got to maybe consolidate databases. Well, it's not just the data warehousing, it's just the usual work. You've got to back up the database, you've got to do reporting, real-time analytics. So all those workloads come in and they start to affect the response time. So within the context of this cloud Exadata platform, what we do is basically the database tags messages that require low latency, log writes, cache fusion messages, locks, et cetera. And then these particular messages bypass all the other messages, stuff like reporting backup that can finish later, it's no big deal. The key thing is you have to accelerate these low latency messages in all the layers. If you just do it, I mean, you've got to do it in the database and the network cards, the switches, and the storage. Otherwise, the bottleneck just moves. If you fix in the database but not the other layers, and things get clogged up at the lower layers. So with that approach, life is good. You can mix both workloads. I'm going to skip this because I want to. Okay, this is one I wanted. Okay. So the last piece of kind of infrastructure-y stuff, a big issue with this, so this architecture works pretty well. We can converge everything, so from the database down to the storage, there's sort of a holistic view of what's happening, but things change. We've gone from, the system was built primarily with disk storage, although flash was available even in the early systems 7 or 8 years ago. Whereas a lot of times we're pretty much using flash 100%. So a lot of these systems just ship with all flash. If you think about it, the issue with flash is it's so fast that this model of shared storage starts to break. So shared storage, we love it because it helps us efficiently share capacity. It's one of the reasons Fibre Channel took off and is still used. It lets you efficiently share capacity, but it doesn't share performance very easily. And in the meantime, look at Fibre Channel cards. Latest PCIe flash is around 5.5 to 6 gigabytes per second. The speed of one flash card is now similar to the fastest SAN link. So a few flash cards to deliver more throughput than a storage array can output. A SAN array, a SAN or LAN can transfer, a server can input. So bottom line is you got this problem is the storage is now too fast. So what this really shows is you can now leverage that advantage I talked to you about with storage servers. You can basically move the request from the database server right down to the storage server. It's processed there. It happens within the storage server side. And what would otherwise have been a huge amount of data that would have to be pumped back to the database server gets processed there. You can also start to do all the cool stuff that Michael mentioned and Stephen around decryption, decompression, compression, et cetera. All right, and with that, I think let's see what time is it. I want to wrap up because bottom line is I could just sort of kind of keep going through examples of how this is pretty cool. But the net of it is what you can do is, again, once you kind of have that vertically integrated understanding of all the layers, you can just start optimizing performance. You can handle failures better. And I could continue to bore you with another 5 or 6 examples of that. But we're going to get to our next speaker. Any questions for me before we go to our next speaker? Boy, it's getting to be the end of the day, but go ahead, yeah. You can either shout it or you can go to the, your choice.
So my question is simple. In all flash systems, so bottleneck is the communication networks. That's true?
I'm sorry, what, could you repeat
In all flash systems, in the all flash system, the bottleneck is just network, communication network.
Yeah, so exactly. We can basically add many more storage servers, and generally for really large queries, like typical of like say a huge scan if you're doing some kind of warehouse or analytics workload. So what we do is we essentially do it on the storage server that has the flash cards. It sort of it does the fast transfers, but on its own internal buses, and then once you've kind of got that final result, more compressed result, that gets sent back across the network.
In that case, if we have some mechanisms, for example, in the all flash, the device has in device computation, like the compression, the response packet or something else. In the case, we can get some advantage in there.
Yeah, but you can, but it sort of happens at typically a lower layer, like at a block layer or a file, kind of a file level. So we're talking like way up at we're doing it really at the database level. So at the very highest, sort of very literally like the application layer.
Thank you.
Okay, cool. All right, any other questions? Okay, great.